absence of the charge on the colloidal particle is an important factor in the stability of the colloidal systems. What is this? Presence or absence? If they are present, what is the magnitude? Means what is its concentration? Means how much is the charge which is having in the colloidal particle is important factors. So we want to stabilize the colloidal systems which are having a longer half-life and stability wise and shelf life expiration period is longer time. We can accomplish by the two means. So one path is providing the dispersed particles with electrical charge. So you are giving electrical charge. Because of the electrical charge, these particles repel each other and they will not be forming as a sediment, even though they are having a Brownian movement for longer period of the time. If they are having a changes in the pH effects, they may be getting sediment. But if you are creating a charge on the particle, they repel each other, they will be long-lasting stability they will be having. This is one. And the second part is surrounding each particle, we need to provide a protective solvent sheath. The sheath will act as a barrier. That barrier which will prevent the aggregation when they are colliding with each other during the Brownian movement. So the sheath will be acting as a small coat of solvent will be preventing when the particle they are moving in a zigzag manner, they tend to hit with the container wherever you are storing it, and they will coming back and hitting to the particle of another which is present in the bulk of colloidal dispersion. During these collisions, they will be mutually adhered, and so if you are providing a protective solvent sheath that prevents the adherence and increases the stability of colloidal system. But the second effect is significant only in the lyophilic colloids, not present in the lyophobic colloids. Reason is they are having lyophobic colloids which are having the system. The system is having a solvent heating, that is they hate the water. So you don't find any sheath of this solvent which is acting as a barrier in the lyophobic systems. But in the second effect is predominant only in the lyophilic systems. Now, you may get the question sometimes why it is solutions are coming here. Don't get confused with the sols and the dispersions. When the particle is completely soluble and the concentration of the colloidal particle is very less, then appear as a sol. Sol means it is a solution, it is a transparent. But you are going to have the Tyndall effect which is present because of the presence of colloidal range particles and molecules in the system. But they are named as a sols. Lipophilic sols generally existing in a solution form only, but the polymer and the surfactant is having a molecular volume which is in the range of colloidal, that is 1 nanometer to 500 nanometers. We are going to have colloidal dispersion properties. First one, we will be seeing about the stability of the lyophobic colloids. In the lyophobic colloids, we have got thermodynamically instability when compared to lyophilic systems, because they are the solution format. They are having a more stability with respect to the physical stability. I am talking. Don't think that they are more stable because to the hydrolysis like that. No, it is hydrolysis stability we will be dealing at 50 unit, that is the stability. But we are looking at now stability of the colloidal dispersions, the dispersion which is getting unstabilized physically. Chemical instability, chemical degradation, we are going to talk in 50 unit. So that is in the later. So lyophobic solutions, lyophobic dispersions are thermodynamically unstable. The particles in each colloidal dispersions, colloids, are stabilized only in the presence of electrical charges on their surfaces, because they don't have any solvent sheath as a protection or the barrier. The lightly charges, they are present on the surface, they produce a repulsion that prevents the coagulation of the particle, enhances the stability of the lyophobic colloids. This is actually a fundamental, we know it. Hence, the addition of small amount of electrolyte to the hydrophobic colloids tends to stabilize the system by imparting the charge onto the particles. So whenever we are having a charge, the charge is very low, Because of the lowness and the very charge is low, then they tend to get aggregate, or they may be having a formation of an aggregation. In that particular case, if you are adding small electrolyte which is having the same charge, they increases the charge. Because of that reason, you are going to have a stability enhanced by Brownian movement. Because of the particle movement, they will be having interactions. They are mainly responsible for the stability of the colloids. There are types of the interaction whenever they are colliding with each other. We know that according to the DLVO theory, which is present in the electric properties of our colloids, we are having two types of interaction. One is van der Waals attraction, another one is electrostatic repulsion. So the van der Waals attraction forces, they cause the aggregation, whereas the electrostatic repulsion, it will cause repelling with each other and enhancing the stability. So when the attractions are predominant, the particle adhere after the collisions and the aggregate is formed. That causes the sedimentation and physical instability. But when the repulsions are predominant, the particles rebound and go back to after collisions, and they remain individually dispersed. So this is the reason we need to make in the lyophobic colloids electrostatic repulsion as the major phenomena to increase the stability. And don't take this is a borderline and bar, and we can apply the same thing for the all whatever we have got. But the concepts for the lyophilic colloids we will be dealing later. It is having a little bit difference, and we need to handle the charge there also. But what is going to happen there, we will see later. But in the hydrophobic, that is lyophobic colloidal systems, we are going to have a stability enhanced by the electrostatic repulsions caused by the increase in the charge of the surface of the particles of colloid. The concentration of the electrolyte necessary to collapse the repulsive force, that is actually permit the aggregation depending upon the valency of the ions and opposite charge. This we have already seen in the Schulze-Hardy rule in the coerced dispersion also. In the coerced dispersion, we have already discussed this. What is happening when you are adding some electrolyte and that electrolyte neutralizes the charge if it is having opposite charge, then the opposite charge, when it is added, the neutralization of the zeta potential is present. Because of that, it is having a neutral charge. Coagulation is occurring because it is not having any repulsive force there. But this is depending upon the valency of the ions of the opposite charge when we are adding it according to the Schulze-Hardy rule. So what Schulze-Hardy rule states? It states that precipitation power of any electrolyte or ion on the dispersed phase of the opposite charge increases with the increasing the valency and charge of the ion. There is one thing is valency. So the valency is monovalent, divalent, trivalent. Another one is the charge which is present on the ion. Even though it is a trivalent ion and one valency is already got neutralized by adding the opposite charge species, only it will act as a divalent. If you are adding some more opposite charge, it will be acting as a some more charge will be there, it will act as a monovalent. It means its charge present on whatever the cation of neutralization of the opposite charge ion, that will decide the what its effect to precipitate the colloid and how it is going to destabilize the system. Now, the higher the valency of the ions according to the Hardy-Schulze rule, the greater the precipitation power. This is GPAT question. Do remember, the higher the valency of the ion, the greater the precipitation power. Because of that reason, when the valency of ion is more, you are going to have less concentration of the particular electrolyte to be added to get the precipitation or neutralizing the surface charge, that is zeta potential. So if you look into that, you can categorize and make in an order aluminum 3+, that is a trivalent ion having a more precipitation power than barium and calcium, that is divalent, and which is having more precipitation power than sodium and potassium, that is monovalent. The same principle what we have already seen in the coerced dispersion. I have already told you at that time we are going to have the same fundamental principle which is applicable to colloidals also. So here also we are going to get, and the same concept you are going to get to exam in both the cases. And in the GPAT, you will be asked in either cases this Hardy-Selje rule and ordering your anions and cations according to their precipitating power, that is based on your charge. Generally, anions will also be having similar effect when divalent anion, that is having a sulfate 2 minus, which is more precipitating power than the chloride and bromide and iodide. Similarly, phosphate, which is having a trivalent ion, which is having a more precipitated power than the sulfate. Now, in the phosphate, say for example PO4 3 minus you have got, it is having more precipitating power. If you are adding some Na salt to it, Na that is alkali, the salt, the PO4 will be neutralizing, it will be forming sodium dihydrogen phosphate, then it will become a divalent. If you are adding some more alkali, then it will neutralize and it will form Na2HPO4, then it will become a monovalent. It means the trivalent phosphate, valency of the phosphate is 3, depending upon its neutralizing to the what extent it has formed, the charge is present in that particular ion and its behavior also similar manner. It means a trivalent phosphate is having a more precipitate power than divalent after neutralization than monovalent. This is an order which is present depending upon the charge of the ion on the electrolyte. So these two concepts, you don't get confused in the GPAT, and you are going to order according to the Hardy-Selje rule. There is no issue for this, and you are able to understand the periodic table concept and valency, and you can answer the question based on this. But there is a little bit some more concept which is present. It is actually a off-mister series. We will be seeing it a little bit later. We will be looking at now stability of Lyophillic colloids. Lyophillic colloids, which we know that it is having a solvent sheet around them. That is a major phenomena in the stability. That sheet is acting as a coat or a barrier to prevent the adherence of two particles after collision in the Brownian motion. Because of that particular reason, we are having a stability of Lyophillic colloids. But if you add electrolyte to Lyophillic colloid, what will happen? If you are adding an electrolyte in the moderate amounts, it does not result in a agglomeration because it is having a solvent sheet protected. That protection of the sheet is still existing. So, but the same thing if you are doing to addition of a similar concentration in the Lyophobic colloid, that will cause changes in the charge and it may coagulate if you are adding an opposite charge. But this will not be that much having in the Lyophilic colloids. So you are going to have a differentiation of the stability with this aspect, that is number one. The second thing is, if you are adding a sufficient salt, even though it is having both the ions, the salt is in the neutral region. Even though it is added, agglomeration and sedimentation of the particle will be resulting in Lyophilic colloids. In the Lyophobic colloids, the salt which we are going to add, it is not going to change. If it is not going to change the surface charge, then it is not going to impact our stability. But in the case of Lyophilic colloids, even though we are adding the salt, which is in the neutral in a manner, even though it is not going to change the surface charge, but it is going to cause the destabilization by aggregation and sedimentation. This phenomena is called as a salting out effect. What is the salting effect? How it is doing the destabilization in the case of Lyophilic colloids, but not in the Lyophobic colloid is the question you may be having in the mind. In general, Lyophilic colloids are stable. Lyophilic colloids are stable because of the solvent state. We have already made it clear. Because of that one, it is they are having the highest stability. If you are adding a high electrolytic concentration, the ions get hydrated. They will be getting hydrated in the place of your colloidal polymer or surfactant, and no water is available for the hydration of the particles. Because of the dehydration of the particle, that results in flocculation and salting out of the colloidal particles. This is actually what the problem is. This results in the flocculation or the salting out of the colloidal particles, which we are having the major problem in the case of our colloidal dispersion of a Lyophilic nature. So in this particular case, what you are going to understand, the charge is not making much effect in the Lyophilic, but depletion of the water by the dehydration of the particle is having a major impact in the stability of a lyophilic colloids, because the solvent barrier, it is getting depleted by addition of a salt in that water. The electrolyte is dissolving and depriving the water to the colloidal particle, making destabilization. This phenomena is called as salting out of a colloidal particles. GPAT question. This concept is a GPAT question. Now, if you see the diagram manner, the solvent sheath of a solvent molecule which are acting as a barrier around the lyophilic colloids, which we are seeing in the extreme left. When you are adding an excess of electrolyte, whether it is a positive or negative, immaterial of neutralization or anything, you are going to take those solvent molecules, and the solvent is forming around your electrolytes and they are getting hydrated. But solvent is same, energy and mass neither be changed or not destroyed. When it is going from a sheath of your lyophilic, it is entering into forming as a layer over electrolytes. It is lyophilic colloid is depleted and it is getting dehydrated. The dehydrated causes the instability. This is actually the major concept in the case of Lyophillic colloids. It means now you can differentiate stability of your Lyophobic colloids and Lyophilic colloids. In the case of Lyophobic colloids, charge is getting affected. If you are adding opposite charge, they are causing a agglomeration because of van der Waals attraction forces. In the case of Lyophilic colloids, you are having a dehydration effect and forming a salting out effect phenomena and making it. In the case of electro-lyophobic colloids, your precipitating power of electrolyte is based on the valency and surface charge. Because of that reason, you have got a trivalent more having a precipitating power than the trivalent. Divalent is having more precipitating power than monovalent anion or cation. In the case of Lyophilic colloid, whether it is an anion or cation, it makes no difference, but it is having dehydration effect. Whether it is having an enhancement of charge or neutralization of the charge, it is not the matter in the lyophilic, but the predominant phenomena is dehydration of the surface, causing the destability and making the system instability and precipitating the colloid. Now, the coagulating power of any ion in the lyophilic system is the ability that ion to separate the water molecules from the colloidal particles. So here, this type of tendency is appearing in the lyophilic system. Now we need to get the guidance from the Hofmeister series or Lyotropic series that ranks the cation and anion in the order of coagulation of hydrophilic solutions. Hydrophilic solutions are they are appearing as the sole systems because they are completely solubilized in nature. Now, in this particular case, you don't have any much concept making it clear, but you need to memorize some of the anions and cations. They are having a precipitating power in the case of lyophilic system, and their ability to dehydrate the particles and separate the water molecules. That is actually a Hofmeister series. If you see anions, citrate, that is a trivalent, which is having more impact than the tartarate, which is divalent, and tartarate and sulfate are both are divalent now, but tartarate is having a more precipitating power than the sulfate. This is one thing which you need to understand. Previously, in the case of Hardy-Sulji rule, we made the valency as the phenomena. Now we are making a differences of a same divalent cations, which is having a differences in their precipitating power and depletion of their water from the solvent sheet. So do remember that tartarate is having a more than sulfate. If you come into acetate, it is a monovalent, but acetate is more having a precipitating power than the chloride. In the Google Forms and your GPAT questions, these questions will be asked in the exam. In your open book exam and your Google Sheets in the sessional, you are going to get questions such things. So because the acetate, which is also monovalent, and the chloride, which is also monovalent, but acetate is having a more power than the chloride to precipitate. Similarly, chloride is having more than nitrate. After that, you are going to have a bromide. At the last, it is iodide. I hope you can understand this with your intermediate background, and you can remember this series like Hofmeister rank or Lyotropic series to study the stability of your colloidal systems. If you coming to cations, if you see magnesium, of course, magnesium is having lesser than aluminum. Aluminum is a trivalent. It is not appearing here, obviously. But if you see the magnesium 2 plus, that is divalent, and calcium 2 plus divalent, when compared to these two, magnesium is having a more precipitation power than the calcium. And calcium is a more precipitating power in the lyotropic series than barium. So these one which we need to memorize, and we need to think in a correct manner that whenever we are adding excipient in our formulation, whether it is a liquid or it may be a vaccine or it may be a serum, you need to use what particular same divalent which is going to have a more stability enhancement. We bound to use sometimes some of the electrolytes. From that also we can calculate and concentration by selecting from the Hofmeister series to enhance the stability of these vaccines and the proteins delivery system in the form of colloidal dispersions and the solutions. Now, if you are going to sodium and potassium, both are monovalent, but sodium is having more precipitating power than the potassium. So this is actually what Hofmeister series or Lyophillic series ranks the cations and anions. You don't have any option. Little bit memory you need to apply it and memorize, and that is the reason I am always saying to you, whenever you are preparing your regular work in a sessional, you need to prepare parallelly for your GPAT, that is GATE, and when you are noting down this type of the series in a piece of paper separately, and that will make you remember before the exam, because you cannot refer a book directly to get back this series, and you want to go back and you don't see, and you know that you have studied it, but you don't know the order in what proportion they are increasing and decreasing. That is the reason you take a piece of paper or a book, in that you write down all points which you tend to forget. And before GATE or GPAT, what you require to do, you are going to read such points only before 1 week, what you have written with your own hand. In that case, what will happen? You will get a memory back. You will understand all the concepts. Your GPAT will be cleared with each without going to any tutorial class. And you need not go to separately coaching for GPAT. So this is actually the logic what you are going to apply for parallel preparation of your GPAT and your sessional and term examinations. Now, if somebody is not having a paper, and do remember that whenever you are entering in the class, try to note down. If you are not noting down, when you are preparing for your exam, don't forget to enter all those points. It will help for your sessionals also, final, your competitive examinations also. Now coming back to some solvents will also be having a depletion of this water, like your alcohol and acetone. They have got a more affinity to the water, and they dehydrate and precipitate the lyophilic colloids. When these are added to the hydrophilic colloids, dehydration of the particle occurs, and the stability of, after dehydration, the stability of the particle depending upon the charge they carry. If they are having an equal charge, which is more, and will be having a repulsion, and it will not form as a sediment, and you are going to have a greater stability. But if the charge is near to neutral, and van der Waals attraction force dominates than the repulsion, then you will get an aggregate. That aggregate will form as a sediment. That sediment will cause the flocculation, and it will be forming instability in the colloidal systems. So the addition of small amounts of electrolytes at that particular time leads to the flocculation or salting out to the colloidal easily. If you are adding some solvents like non-organic solvent like alcohol, acetone, if they are also having a charge. And you may get the question, sir, why should we add alcohol there? Sometimes you tend to add this to solubilization of your drug, or it may be acting as a preservative. It will be acting as a antimicrobial preservative. Sometimes you bound to add it. At that time you have got such effects. You need to remember that when you are making a colloidal dispersions. Another phenomena is called as a co-acervation. Don't get confused. In the pharmaceutical technology, you have got a co-acervation for the particle coating and coating of your tablets. In that, your coating layer is getting precipitated onto the tablet and a particle and giving the coating. The phenomena you might have already studied or going to learn in the 5th sem. But now, when you are adding a negatively charged and positively charged hydrophilic colloids, here you are not adding any electrolyte. You are adding, it is also having a charged species of opposite charge in nature. Both are hydrophilic colloids only. What will happen? This is actually the question, because till now whatever we have learnt, electrolyte. In the effect of electrolyte on the Lyophillic system, we have seen first solvent sheath effect, depletion, and second is the charge. In this particular case, when you are not adding electrolyte, you are adding another colloid of opposite charge. Then what will happen? The particle may separate from the dispersion to form a layer rich in the colloidal aggregate. That aggregate it will be causing a instability in the system. It means we cannot mix two colloidal systems which are having the opposite charge. If you do that, the colloidal rich layer which is formed, that is called as a co-acervate. That co-acervate will be separated and you will be getting a supernet clear liquid that causes the easily to the visible eye. You will be having, knowing that your colloidal dispersion is unstable and it got physical instability. You need not to use the microscope also, directly with the naked eye you can see. But generally for the, you are seeing dark field microscopy for the Brownian movement, and you are going ultra microscope to see their movement of the Brownian motion. But in the case of co-acervate, you are going to have this colloidal rich layer is separated from the rest of solvent you will be getting. The phenomena in which macromolecular solution separate into two layers is referred as a co-acervation, and the layer which is formed is called as a co-acervate. In this particular case, we are adding oppositely charged hydrophilic colloids. As an example, we can take, one example is that you take the gelatin solution and acacia solution, both are water soluble in nature, they are getting present in the clear solution forms. But if you are taking the gelatin at pH below 4.7 and it is the isoelectric point is 4.7, you know that the isoelectric point is the point at which the functional groups which are present in that, which is having a unionized state and making them precipitated. It means at the isoelectric point, any protein will be having a least solubility. Say for example, you have got a zwitterion. In the zwitterion, you have got both amine group and carboxylic group. If its isoelectric point is 4.7, if you are having that at a particular isoelectric point, the precipitate formation is going to be very high. But in this particular example, gelatin isoelectric point is 4.7, we are knowing that. So it is having a precipitate. So we want to make a solution form below that. Say for example, below 4.7, it is actually a positively charged. When it is having a positively charged, you are adding acacia, which is having a negatively charged at that particular pH. Both negative and opposite charge which are present in the gelatin and acacia at 4.7, that is below 4.7, which is going to cause the precipitation, that is a co-acervate. So when the solutions of these colloids are mixed at a certain proportion at the particular pH, and you will be getting a co-acervation. And the viscosity of the upper layer, now it is poor in colloid and it is markedly decreased, and it is appearing as a stagnant and it is having a clear supernet liquid. Whereas the lower layer, which is having a pitch in the co-acervate, its viscosity is very high, it is getting separated. This is actually what you are going to get an instability because of the co-acervation in the hydrophilic system. When you are mixing oppositely charged positively and oppositely charged negatively charged hydrophilic colloidal systems. Now we are going to enter into the protective action of the colloid. In the protective action of the colloid, we can tend to get some addition of some, when large amount of the hydrophilic colloid carrying opposite charge is added to the hydrophobic colloids. Previously what we have done, we are adding hydrophilic colloid and opposite colloid which are having opposite charge. We have seen the co-acervation. Now we are going to have a different phenomenon. When the large amount of hydrophilic colloid is carrying opposite charge to the hydrophobic colloids, these gets adsorbed onto the hydrophobic colloidal particles, form the protective layer around it. This will be having a prevention of sediment, prevention of stability, problem in the lyophobic colloids. It means lyophobic colloids can be stabilized by adding large amount of hydrophilic colloid which is having opposite charge. But do remember, in this particular case, GPAT, you will be getting confused. When you are getting added large amount of electrolytes of opposite charge, you will be getting neutralization and making the separation possible. If you are adding too much of X and you are going to have again surface charge is present and it is causing a deaggregation and you are going to enhance the stability. But in the case of your addition of hydrophilic and hydrophobic colloids, that will form as a protective layer around it. So this absorbed layer prevents the precipitating of ion and reaching the solution stages of the particles and making it a solvent sheet effect also present onto the lyophobic colloids also. Therefore, coagulation is prevented and the systems become stabilized. This is actually called as a protective action of a colloid system, where we are adding a lyophilic colloid as a protectant to stabilize highly unstable, thermodynamically unstable colloidal system, that is lyophobic colloid. The entire colloid behaves like a hydrophilic colloid only, and the lyophobic colloid will be behaving, it's losing its behavior because it is getting a solvent sheet. Below that you have got hydrophilic colloid. So the colloid that helps the stabilization of other colloid is known as a protective colloid. This is actually what you will be having a separate question in the 5 marks, protective action of a colloid. Do remember these points, you can easily answer. And when you are able to see the concept of zeta potential and your DLVO theory and solvent sheet effects, you can answer all these questions and concepts, and you can attempt GPAT also very well. In the diagrammatic manner which is represented here, if you see the hydrophobic colloid which is having a positive in nature in the extreme left. So the positively charged particles, they are present as a dispersed stage. You are going to have in a dispersed stage. But when you are going to have any electrolyte added to it, then it will be causing a destability by neutralizing it. But when you are having a large quantity of hydrophilic colloid, that is having another colloid which is having opposite charge, then it will be acting as a protective action. So this protective action you are going to get as a coating which is forming onto the hydrophobic colloid by the hydrophilic colloid, and it is acting as a protective colloid, and it is absorbed and making it more stable than whatever which you have got observed. Okay, so this is the concept which we are going to use it to enhance the thermodynamically unstable system called as a hydrophobic colloidal system. Don't get confused. I am telling sometimes lyophobic, sometimes hydrophobic. When the water is a solvent, we call them as a hydrophobic system, and when it is any another solvent is used other than the water, we are calling it as a solvent, that is lyophobic system. There is another way is you are having a this negatively charged hydrophilic colloid is present, and you are having a positively charged addition of the electrolytes even at the higher concentration. At that particular case, the most stable ion cannot reach the colloidal particles and no coagulation is observed because of this protective action. So this protective action which is making a charge depletion and making a agglomeration, and the colloid will behave as a hydrophilic in nature only, not the hydrophobic action because of the protective action. After this protective layer is formed, then even if you are adding electrolytes more, and it will not cause the damage, and it will not cause the solvent sheet depletion effect, it is charge depletion effect, and it will not cause any instability. Because of this reason, you are enhancing the stability of thermodynamically unstable hydrophobic colloidal system by Lyophillic colloid, that can be more stabilizing even after addition of the electrolytes also. It can withstand without having a salting out effect. This is actually major phenomena and you are going to use it for the protection sometimes, which will be required in R&D systems whenever you are doing as a as a project. You think that you are going to enter into the pharmacy final year, you are going to have a project. Do remember that this such type of work you can take it and you can see and how to make this colloidal system enhanced, because nowadays whatever we are going to use hormones and your vaccines and everything is a protein systems. They are having a deuterionic effect and they are going to have behavior as a colloidal systems only. These concepts are going to be a minimum weight in the mg, minimum weight, that I am adding very less quantity of a protective colloid, that is in the case of hydrophilic colloid, and the dry weight basis of a dispersed phase required to prevent the color change from the red to violet in the 10 ml of gold solution on the addition of 1 ml of 10% solution of sodium chloride. So this is actually what the gold number is. So the gold number for the some commonly protective colloids are given. So this is actually for the gelatin. You are going to have gold number 0.005 to 0.01. Then what is this number? You may get the question. You are having a gelatin solution. You are having it. That gelatin solution, you are having a minimum quantity that is added to give the protective action to the lyophobic colloid. So the lyophobic colloid is in this particular case is the gold solution. It is given as gold. It is gold solution. That is solution. It is means a gold colloidal solution. After addition of 1 ml of 10% solution of monovalent cation and anion is present in this particular case, and in spite of that addition of electrolyte, and it will not have any instability by adding 0.05 to 0.005 to 0.001 in mg to the dry weight of your dispersed phase, whatever which you are going to have. So in the when you are having a lesser and lesser quantity, you are adding it. It means you are getting a better and better quantity, stability you are going to make it. Say for example, if you are seeing albumin for albumin, it is having a gold number 0.1. It means gelatin is better than albumin, and acacia is having a gold number 0.1 to 0.2. Basically, the gold sol, don't get confused with the sol and the colloidal here. Gold is also appearing as a colloidal only. That when the lower concentration, we are calling it as a sol. It is a hydrophobic colloid. It has a red in color. When it is having a red in color, when it is converting into bigger sized particles, then it will convert to a violet in nature. Why this is taken as a thumb rule? Why this gold colloid is taken for the determination of gold number is, you need not use any dark field microscopy for determination of conversion of your hydrophobic colloid to hydrophilic colloids and stability systems. Just you can see by the change in the color with the naked eye. Because of that reason, this gold number concept has come into the existence. When the electrolyte like sodium chloride is added, coagulation of the colloid is observed without the addition of your hydrophilic colloid. When you are adding hydrophilic colloid, then what will happen? This red color will not convert into a violet. It means it is appearing as a stable. It means how much less concentration I am going to add in such a way that my red color of gold solution is maintained as such without converting into violet with a naked eye. So I need to repeat different hydrophilic colloids like gelatin, albumin, and acacia. These are all we are added in a small mg quantity. And we are going to see that which is having a better beneficial effect for the protective action. When the protective action of colloidal are added, these stabilize the gold solution and prevent the change to violet color. Lower the gold number, greater the protective action. This is your GPAT question. You are having a lower the number means a small amount is required to protect your hydrophobic colloid, which is having a better stability. It means you are adding a less excipient or less quantity of your hydrophilic colloid to stabilize your system. It is better, and you are having a cheap also, and it is economic also. So that is the reason. Go lower the gold number, greater the protective action you are going to observe. I hope you have already